Professor Seham Khan, Executive Dean, Faculty of Health Sciences, Professor Nicolette Houreld, our inductee this evening, Professor Heidi Abrahamson, our respondent and Director of the Laser Research Center, and DST NRF Sarchi Chair for Laser Applications in Health, senior leaders of the university, members of Senate and other academics, distinguished guests, ladies and gentlemen, Sanibonani, Goeienaand, good evening, Thobela. It is indeed a great honor and a special privilege for me to welcome you to the Professorial Inaugural Lecture of Professor Nicolette Houreld. As I do so, I wish to express a warm welcome to her loved ones, special guests, and her colleagues. This is indeed a proud and joyful, yet a landmark moment for all of you, for Professor Houreld, and of course for us here at the University of Johannesburg and higher education in South Africa and beyond. The inauguration of professors is a public ceremony in which newly appointed professors are inducted into office by the Vice-Chancellor and deliver their inaugural addresses. The ceremony has its roots in the medieval university and serves multiple purposes. Firstly, it is an expression of welcome and an entry for new professors joining the circle of colleagues who are already professors. Secondly, it provides a platform for professors to display their expertise in the discipline and showcase their research. In isiXhosa we say, ukuthweswa isidanga kwisigaba sobujingalwazi. This, loosely translated, refers to assuming the role of the professor. Of course, in colonial traditions subscribed to by universities, this refers to the gown and the cap. Traditionally, the wise one would accept a blanket, ingubo. Once we have listened to the inaugural address, the gown or ingubo, denoting the professorship, will be formally assumed. Today, we gather to bear witness to the entry of Professor Houreld to the illustrious community of scholars at the university. It is a celebration of the contributions to the discipline and ultimately the impact on society. Professors provide a university with its identity, character, and academic legitimacy and integrity. The inaugural lecture is a rite of passage following the confirmation of the appointment of the person as a professor. This evening, we will listen to Professor Houreld as the gown goes to town. By this, I mean the power of the inaugural address is when the expertise is showcased beyond the corridors of the university and reverberates with society. It stands out as a moment of pride for the incumbent, the family, fellow scholars, the university, and ultimately society. For the German philosopher and diplomat Humboldt, a university referred to the whole community of scholars and students engaged in a common search for truth. Newman talked about teaching universal knowledge. Recently, universities have been viewed as instrumentalists serving the purpose of the economy or utilitarian in purpose. I would hope that we can break out of these narrow conceptualizations and reflect on the university as contributing to the public good. Edward said in an article on defiance and taking positions, offers a formulation of the ideal role of a true intellectual as, open quote, one who commands a vast knowledge of his or her discipline, who is rigorous in the analysis of literature, who views being an intellectual as a vocation, the intellectual who considers it necessary to step into the public sphere and to speak truth to power, namely to question, interpret, and understand authority rather than consolidating it. To step out of the boundaries of the academy to connect oneself, to affiliate oneself, to align oneself with an ongoing process or contest of some sort, perhaps with the aim of improving the lot of the oppressed. The intellectual who functions as a kind of public memory to recall what is forgotten or ignored, to make the connections that are otherwise hidden, and to provide alternatives for mistaken policies, close quote. It remains then for us as a university with a Pan-African vision to derive our mandate as intellectuals and as professors. How do we, I apologize, embrace the role of a professor as a disruptor while continuing to be flagship carriers of our discipline? This evening, we will listen to Professor Houreld as one further step in the journey of being a professor. This is a journey which does not culminate once this lecture has been given. It is a self-reflective pause in the journey of the professor with a promise of more to enrich our minds and simultaneously contributing to the rich intellectual body of work in the discipline. Let me now invite the Executive Dean, Professor Siam Khan, to introduce Professor Houreld. I thank you. Rialebuha, Siabonga, Bayadanki.
Good evening. In 1998, Nicolette Houreld completed her first higher education qualification, the National Diploma in Biomedical Technology from the former Technikon Witwatersrand. She then went on to complete her BTech and MTech degree. She went on to pursue a doctoral qualification under the supervision of Professor Heidi Abrahmse in the field of photobiomodulation and graduated with a doctoral degree in biomedical technology from the University of Johannesburg in May 2007. She then conducted a 2-year postdoctoral project in the same field of research. Nicolette took up the position of lecturer at the University of Johannesburg in 2009 and moved through the academic ranks from lecturer to senior lecturer, associate professor, and now professor. In 2016, she was appointed as the deputy chairholder to Professor Heidi Abrahmse, the SACHI chairholder in laser applications in health. Nicolette received her Y2 NRF rating in 2012 and is currently a C1 rated scientist with a Scopus H index of 23. 2021 is now Nicolette's 12th year in higher education at the University of Johannesburg. During this time, Nicolette has served on several academic committees, including the Faculty Higher Degrees Committee, the Faculty Research Ethics Committee, where she is also the Deputy Chair of the REC. She has recently been appointed as the Senate representative on the Senate Research Ethics Committee. Her international standing and contribution to the field of photobiomodulation are well recognized, as is seen by her position on the Executive Committee of the World Association for Photobiomodulation Therapy, WALT, since 2010, first as treasurer, then as vice president, and now as president-elect. She also serves on the editorial board of the International Journal Photobiomodulation, Photomedicine, and Laser Surgery. Nicolette's contributions to the scientific development of the field of photobiomodulation have included over 100 scientific publications, which are all well cited. She has supervised numerous postgraduate students at a master's, doctoral, and postdoctoral level. Her current research focus is on the molecular and cellular effect of photobiomodulation on diabetic wound healing. Thank you.
Dear Vice-Chancellor and Principal of the University of Johannesburg, Professor Talitsi Marwala, VC Functionary, Professor Mpedi, Executive Dean of the Faculty of Health Sciences, Prof Siam Khan, Director of the Laser Research Center and DST NRF Saatchi Chair for Laser Applications in Health, Professor Heidi Abramser, University of Johannesburg Management Executive Committee, colleagues and students of the University of Johannesburg, family, friends, and invited guests. Thank you for joining me tonight in celebrating this prestigious moment in my career. Before I start my address, I would just like to say a special thank you to everyone who has walked this path with me and contributed to who I am today. Firstly, to my family. My appreciation goes to my parents, Colleen and Mervyn. Thank you for everything you have done for me and that you continue to do. I am so much as a result of what I've learned from you. To my sister Jacqueline and your family, you have always stood by me and encouraged me, and you've always been my biggest fans. To Gary, who has put up with me for the last 17 years, for all your support you have provided and the sacrifices you have made. To Jill and Mike, for all of your support and help with Gemma. To my dear daughter Gemma, and of course Taylor. I'm so grateful to have you in my life and for all the sacrifices that you have made. To all my friends for trying to pretend that you actually know what it is that I do and what it is that you think I do. And all the weird questions that I sometimes get along with that. To my UJ family and to all the colleagues in all the different departments and to all the LRC staff and students, past and present. Without your support, hard work, dedication, none of this would have been possible. I'm very grateful for all of you and for all of your hard work, and I'm very proud of the LRC family. To all my teachers, mentors, and collaborators, there are too many of you to mention, but I'd like to make special thanks to Professor Heidi Abramser. You have been my supervisor, my mentor, a colleague, and a friend for many years. You have shared so much of yourself with me, and I'm very grateful for this journey that you've walked with me. To my two mentors as part of the UJ Academic Accelerated Mentorship Program, Professor Andre Swart and Professor Mari Puchumpool, for all of your support over the years, and to Prof Siam Khan for your support and kind words. In this lecture, I'm going to provide you with an overview of the research that I've been involved in over about the last 14 years in the Laser Research Centre. This research is involved in photobiomodulation, or PBM, and its focus is in wound healing, and more specifically in diabetic wound healing. Diabetes mellitus is a chronic, long-term metabolic disorder which occurs when the body does not produce any insulin, referred to as type 1 diabetes, or when insulin is produced but the body cells are resistant to the insulin that is produced, or type 2 diabetes. This decrease or impairment in insulin results in elevated blood glucose levels. The estimated global prevalence of diabetes in adults aged 20 to 79-year-olds is 463 million, and this figure is expected to rise by 51% to 700 million by the year 2045. Approximately 79.5% of people with diabetes live in low and middle income countries. In Africa, the estimated number of people with diabetes stands at 19 million, and it is estimated that this number is going to increase by 143% to 47 million. The highest prevalence of diabetes in adults in the African region is in South Africa, with an incidence of 12.7%. Globally, diabetes is among the top 10 causes of death, and approximately 4.2 million adults were estimated to have died as a result of diabetes and its complications in 2019, and this amounted to 89,800 deaths in South Africa. People living with diabetes are at increased risk for developing serious health complications, and there's an increased need for medical care, reduced quality of life, and undue stress in families. Wound healing is a well-orchestrated integration of complex biological and molecular events involving a variety of cell types, cytokines, and growth factors. There are 4 phases to wound healing. First phase is coagulation or hemostasis, where there's formation of a blood fibrin clot and release of various growth factors and cytokines. Second phase is inflammation, which involves cell recruitment and chemotaxis, which is the chemical attraction of cells to the wound area. There's also wound debridement to remove any dead or damaged tissue. Third phase is proliferation or migration, where in this phase it largely involves angiogenesis, which is the development of new blood vessels. There's deposition of the extracellular matrix, which is the surrounding support structure for cells such as collagen. And there's also wound contraction in an attempt to close the wound. The fourth and final stage is remodeling, and this is where you get scar formation. Chronic wounds don't progress through these normal stages of wound healing, often getting stuck in one or more of these phases. A wound that extends for longer than 3 months is then termed chronic. Long-term side effects of diabetes includes microvascular complications, where the small blood vessels are affected, commonly impacting the eyes, kidneys, and nerves, and microvascular complications, where the large blood vessels are affected, commonly impacting the brain, heart, and lower extremities. Approximately half of all diabetic patients have some type of diabetic neuropathy or nerve damage, which often affects the nerves of the feet and the lower legs. This nerve damage results in loss of feeling in the feet, such that diabetic patients become unaware of small cuts, sores, or blisters on their feet. Nerve damage and poor blood flow puts diabetic patients at risk for developing a diabetic ulcer. Diabetic foot ulcers commonly go undetected for long periods of time and frequently become chronic, non-healing wounds. These wounds are typically stalled in the inflammatory phase of wound healing and very rarely progress beyond this stage without any medical attention. Diabetic foot ulcers are at increased risk for infections and developing gangrene, often necessitating amputation. Lower limb amputation in people with diabetes is 10 to 20 times higher than people without diabetes, and globally it's been estimated that a limb or parts thereof is lost to amputation every 30 seconds as a consequence of diabetes. Treating diabetic foot ulcers is challenging, requiring specialized treatments by a multidisciplinary team. And once healed, these wounds are frequently considered high risk for recurrence. This brings us to photobiomodulation, or PBM, which has seen positive results in the treatment of diabetic foot ulcers. PBM is a non-invasive, non-thermal treatment modality which involves the application of light at specific wavelengths to living tissue and cells to induce photophysical and photochemical effects at various biological scales. PBM involves the use of low-level, non-ionizing forms of light from sources such as lasers, light-emitting diodes or LEDs, and broadband light using the appropriate filters in the visible red or in the visible and near-infrared electromagnetic spectrum. The term low level is frequently used because the light that is used is of a very low energy density or fluence, and it has a very low, because it has very low energy density and very low irradiance. So it shouldn't be confused with other forms of laser therapies which make use of very high-powered light, such as in laser hair removal and in laser tissue resurfacing. At the most basic level, PBM induces a photochemical reaction in the cell, and it can be likened to photosynthesis in plants, vitamin D synthesis, or sun tanning, or the use of blue light for neonatal jaundice. All these processes involve chemical reactions in response to the absorption of light. The mechanism of action associated with PBM is still questioned, and it's most likely several mechanisms can be involved depending on the target and the type of cells which are being modulated. In order for anything to happen, the light has to first be absorbed by the treated cells, and the most published and recognized mechanism of action is that of cytochrome C oxidase, or COX, which is an enzyme found in the inner membrane of the mitochondria and forms part of the electron transport chain. The mitochondria is often referred to as the powerhouse of the cell and is responsible for the production of energy in the form of ATP, or adenosine triphosphate. COX transfers electrons from cytochrome C to molecular oxygen, contributing to the production of ATP. ATP is a central metabolite that provides energy to drive various cellular processes, and itself is an important cellular signaling molecule. It has been shown that COX is able to absorb light in the red and near-infrared spectrum and leads to the production of ATP. Under stressed or ischemic conditions, which is where there's reduced oxygen in the tissue, mitochondrial nitric oxide displaces oxygen, thereby reducing cellular respiration and ATP production. When light is absorbed by COX, there is a photodissociation of nitric oxide from COX, meaning that the COX that is associated or bound to the nitric oxide releases that nitric oxide, allowing oxygen to bind to the COX, and then you get increased ATP production. Oxygen acts as a final electron acceptor in the electron transport chain, and in the process is converted to water. Part of the oxygen that is metabolized produces reactive oxygen species, or ROS, as a natural byproduct. ROS are chemically active molecules and play a very important role in cell signaling at very low quantities. PBM promotes the metabolism of oxygen and also acts to increase ROS production in small quantities. Mitochondria also plays a role in the storage and hemostasis of cellular calcium. The concentration of cellular calcium regulates several reactions and is important for signal transduction. An increase in this intracellular calcium has been seen in response to PBM. All these mechanisms lead to downstream intracellular effects, leading to gene transcription or activation of genes leading to protein synthesis. There is also increased production of essential cytokines and growth factors. Some of the chemical effects which have been observed, or clinical effects which have been observed in response to PBM, include increased angiogenesis and neovascularization, which is the formation of new blood vessels, increased collagen production, increased muscle regeneration and decreased muscle atrophy, which is the wasting away of muscles, decreased inflammation and edema, which is swelling in tissues, increased nerve regeneration, cartilage production, and increased bone formation. So there's an increase in a range of various tissues types, and there's also an analgesic effect, which causes a decrease in pain. In PBM, an optimal choice of parameters must be used to get the desired effects. These include things like the correct wavelength, the correct fluence or energy density, the correct irradiance or power density, pulse structure, and irradiation time. And it has been well established that if light is applied, is it not of sufficient irradiance, or the irradiation time is too short, then there is no response. If the irradiance is too high, or the irradiation time is too long, then you get inhibition. And somewhere in between is where you get stimulation. The depth at which light penetrates target tissue is dependent on the wavelength, with longer wavelengths penetrating deeper into tissue. Effective tissue penetration of light occurs around wavelengths of 600 to 1,200 nanometers, the so-called optical window. Blue or green light below 600 nanometers is absorbed by pigments in the tissue or in the skin, such as melanin and hemoglobin, while wavelengths above 1,200 nanometers is absorbed by water. In wound healing, wavelengths in the visible red spectrum and near-infrared light is used. Visible red light in the range of 600 to 700 nanometers is used to treat superficial tissue, while longer wavelengths in the range of 780 to 950 nanometers, which penetrates further into the tissue, is used to treat deeper-seated tissues. I'm going to give you an overview of some of the research which has been conducted over the last 14 years or so in the Laser Research Centre within the wound healing niche. This work has been conducted in various cell models, in vitro, meaning outside of a living organism. Cell models used ranged from normal, unstressed cells to wounded, where a wound was induced by the scratch assay, to diabetic wounded, where we induce diabetes by growing cells in a hypoglycemic environment, so we add more glucose to the culture media, and then also hypoxic models where cells are grown without oxygen and without FBS or fetal bovine serum, which is the nutrients for the cell. Most of these studies concentrated on light in a visible red wavelength at 660 nanometers, as well as near-infrared light at a wavelength of 813 nanometers, and a variety of biological assays were tested. This is a time-lapse video showing how fibroblast cells actually grow and migrate from the wound margin into the central scratch over a period of 48 hours. You can see how the cells are trying to cover that wound area, or that central scratch or the wound in a Many of our earlier studies focused on determining the optimum parameters that I spoke to you about earlier on. And we used visible red light using a helium neon laser at 632.8 nanometers, near-infrared diode laser 830 nanometers, and an ND-YAG laser at 1064 nanometers. Two fluences were used, 5 and 16 joules, and irradiated cells once or multiple times. And what we found was that a wavelength in the visible red and near-infrared range gave optimum results, using a fluence of 5 joules per centimeter squared. In this study, we irradiated cells at 830 nanometers with 5 joules per centimeter squared and determined cellular viability, proliferation, apoptosis or programmed cell death, and pro-inflammatory cytokines interleukin-6, interleukin-1 beta, and tumor necrosis factor alpha. We also looked at nitric oxide and reactive oxygen species. On the left-hand side of the graph, the results show that irradiation resulted in decreased caspase 3,7 activity or decreased apoptosis. On the right-hand side of the graph, we can see that there's an increase in proliferation and viability in the wounded models. There is also a decrease in pro-inflammatory cytokines, tumor necrosis factor alpha, and interleukin-1 beta, as you can see on the table on the right. 15 minutes post-irradiation, there was an increase in nitric oxide, which we can see in the graph on the left by the grey bars. And then there was also an increase in reactive oxygen species, which can be seen by the fluorescent image on the right. The green fluorescence is the reactive oxygen species, and the little blue circles is the cell nuclei, which have been stained with DAPI. The effects of 660 nanometers and 830 nanometers with 5 joules was determined on collagen and extracellular matrix proteins. Here we looked at collagen type 1, matrix metalloproteinase MMP 3 and 9, and these are enzymes which degrade the extracellular matrix as well as collagen. We looked at tissue inhibitor of MMP or TIMP1. In this graph, the solid black bar on the far left represents non-irradiated control cells. The grey bar in the middle represents cells irradiated at 660 nanometers, and the white bar on the right-hand side represents cells irradiated at 830 nanometers. If we look at the first graph on the left, which represents collagen type 1, we can see that there's a decrease in the diabetic wounded, hypoxic wounded, and diabetic hypoxic wounded cells as compared to the normal cells. And this is what one would expect to see because there's decreased collagen production in patients with diabetes. However, when we irradiated these stressed cells at 660 or 830 nanometers, there was an increase in collagen. When we looked at TIMP1, we can see that is the inhibitor of the MMPs, those enzymes that degrade the collagen. After irradiation, there is an increase in the diabetic wounded and diabetic hypoxic wounded cells. When we measured the matrix metalloproteinases, these are the ones that degrade the extracellular matrix and collagen. MMP3 is seen on the graph on the left, and MMP9 can be seen on the graph on the right-hand side. There was a significant decrease in these enzymes post-irradiation. So these results showed us that PBM not only increased collagen, but also decreased the enzymes that degrade them and increases the inhibitor of these degrading enzymes. In addition to looking at collagen production, we also investigated PBM at 660 nanometers with 5 joules on the expression of genes that code for numerous extracellular matrix proteins. The results from the study were overwhelming. An irradiation of diabetic wounded cells resulted in the upregulation or the turning on of 18 genes and downregulation of 31 genes. There's too many genes to discuss, but what I do want to say is that there were genes for various collagen types which were upregulated. Cellular adhesion molecules were upregulated, and the cellular adhesion molecules is the protein that sort of connects cells or attaches cells to each other. So those were all upregulated, and then our MMPs were downregulated. A similar study was repeated using a wavelength of 830 nanometers, and here the genetic profile was very different. Here we saw 7 genes which were upregulated, or 5 genes were upregulated and 17 genes were downregulated. And these two studies showed that PBM stimulates the expression of genes involved with cellular matrix proteins, and that you would get different profiles using different wavelengths in the same cell models. When we looked at the effect of 660 nanometers on enzymes involved in the electron transport chain, here we isolated mitochondria, so we didn't irradiate whole cells. These isolated mitochondria were irradiated, and then we looked at the enzyme kinetics, or the activity of the enzymes. And here we looked at enzymes complex 1 to 4. The results showed that there was a significant increase in enzyme activity in complex 4, which is our cytochrome C oxidase, or COX. The same wavelength was then used to irradiate cells and look at some of the genes that are involved in these enzyme complexes. We found that genes for complex 1, 4, and 5 was upregulated or turned on in normal wounded cells. In the diabetic wounded cells, genes coding for complex 4 and 5 were upregulated. And in the ischemic cells, genes for complex 5 was upregulated. These two studies showed us that that PBM at 660 nanometers and a fluence of 5 joules not only increases the activity of the enzymes involved in the complex electron transport chain, but it also increases the gene transcription of these proteins. We then focused our studies on specific cellular pathways. We knew that PBM could increase cell migration, increase proliferation and viability, but we weren't sure what cellular pathways was involved in this. The first pathway we looked at was the JAK-STAT pathway, which was done at 660 nanometers with 5 joules. Before we get into the results of the study, I need to briefly explain to you what JAK-STAT is and how it works in response to epidermal growth factor, or EGF. EGF is a growth factor and is known to be decreased in diabetic ulcers, and they also have a dysregulated JAK-STAT pathway. JAK, or Janus kinase, is an enzyme that can transfer a phosphate group from ATP to the tyrosine residues of specific proteins inside a cell. It functions as an on-off switch for many cellular functions. STAT, or signal transducer and activator of transcription, are latent transcription factors, meaning that they're always present in the cell in a dormant state, and they need to be turned on. And when they are turned on, these factors will translocate or move to the cell nucleus, where they activate the transcription of specific genes. EGF binds to its receptor, EGFR, and this induces receptor dimerization, meaning the membrane proteins move laterally towards each other within the cell membrane. There is also autophosphorylation of JAK2, which means a phosphate group binds to JAK, activating it. When this happens, STAT1 and STAT5 will get phosphorylated or activated. They will dimerize, meaning they will come together, and then they will translocate or move to the cell nucleus, where they will stimulate the transcription of various genes. The results show that when we irradiated our cell models with PBM at 660, there was an increase in the release of epidermal growth factor, as can be seen by the dark grey bar on the left-hand side, on the left graph. And when we looked at the phosphorylated EGFR, which is on the graph on the right-hand side, again looking at the grey bar in the middle, there was an increase in this phosphorylated receptor, meaning that the receptor had been activated or turned on. When we measured activated phosphorylated JAK2 in response to laser irradiation, there's a significant increase in the wounded, diabetic, and diabetic wounded cells, as again seen by the increase by the grey bar in the middle. When we measured the phosphorylation of STAT1 and STAT5, STAT1 is on the graph on the left and STAT5 is on the graph on the right. And there was an increase in all cell models, including diabetic wounded cells. When looking at the downstream effects of our JAK-STAT pathway, we looked at migration and proliferation. And we could see that there was an increase in migration, as shown on the graph on the left-hand side. The graph on the right-hand side shows the proliferation of cells, and when we irradiated them, there's a significant increase in proliferation. We also looked at genes involved in the JAK-STAT pathway in response to photobiomodulation at 660 nanometers using a PCR array, which looks at 84 genes that are involved in the JAK-STAT pathway. These are only a few select genes that we looked at, but overall 46 genes were upregulated or turned on, and 27 genes were downregulated. From these results, we could see that there was an upregulation of the EGF receptor, EGFR, as well as JAK1, 2, and 3. There was downregulation of SOX, which is an inhibitor of the JAK-STAT pathway. And there was upregulation of STAT1, 3, 5, and 6. We could conclude from these studies that PBM at 660 with 5 joules promotes cell proliferation, migration, and survival in our wounded diabetic cells in response to EGF, which gets released by the cells and stimulates the JAK-STAT pathway. We looked at the differentiation of fibroblasts into myofibroblasts in response to PBM at 660 nanometers with 5 joules per centimeter squared. In diabetes, diabetic fibroblast cells become senescent, meaning that the cells are no longer able to proliferate or differentiate, but they are still alive. A fibroblast cell will differentiate into a protomyofibroblast and then into a myofibroblast, which is involved in the contraction and remodeling of the extracellular matrix. The fibroblast cell marker Thi1 was measured at 24, 48, and 72 hours post-irradiation. Our control cells here are represented by the solid grey bar and the irradiated cells by the light grey bar with the lines in it. There was a decrease in Thi1 in diabetic wounded cell models 24 hours post-irradiation as compared to the control cells. This decrease continued over a period of 72 hours where it was virtually unmeasurable in the irradiated cells. This indicated to us that the fibroblast cells were in the process of differentiating. This is a fluorescent image of diabetic wounded cells that have been fluorescently labeled with antibodies against Thi1 and is stained red. The blue circles is our cell nuclei which have been stained with DAPI. The line at the top is the non-irradiated control cells, and the line at the bottom, or the images at the bottom, is the irradiated cells. And you can see that there's more red fluorescence in the irradiated cells at 48 hours than there is the non-irradiated, and less fluorescence at 72 hours. So these cells are differentiating a lot faster than the non-irradiated cells. We also measured EDA fibronectin, which is a marker of our protofibroblasts, and levels were significantly increased at 72 hours. This is the fluorescent image of the EDA fibronectin, which is stained in green. And here we can see the irradiated cells are at the panel at the bottom, and there's more green fluorescence at 24 and 48 hours, and less fluorescence at 72 hours, as compared to the control cells, which is in the panel at the top. At 24 and 48 hours post-irradiation, diabetic wounded cells showed a significant increase in alpha smooth muscle actin, which is the marker of myofibroblasts. This is the fluorescent image of the diabetic wounded cells staining for alpha smooth muscle actin, which is stained in red. This is the last study that I'm going to show you. Here we looked at the influence of photobiomodulation at 660 and 830 nanometers on oxidative stress by studying 4-KED family of transcription factors class O subtype 1, or FOXO1. We also looked at protein kinase B, or AKT, enzymic antioxidants, superoxide dismutase, catalase, and heme oxygenase. Enzymatic antioxidants break down and remove damaging free radicals, thus reducing oxidative stress. And our diabetic patients have a lot of diabetic or oxidative stress, which contributes towards the chronicity of their wounds. This diagram represents the AKT FOXO cellular pathway. AKT plays a central role in cellular functions such as cell proliferation and survival. Increased levels of AKT causes a decrease in FOXO levels, which directly attenuates oxidative stress to maintain proliferation and migration and to promote wound healing. Irradiation of the cell models, including diabetic wounded cells at both 660 and 830 nanometers, resulted in significantly increased AKT levels, as indicated in the top graph. And there was decreased FOXO levels, as indicated in the graphs at the bottom. Control cells are represented by the white bar. Cells irradiated at 660 nanometers is shown by the dark grey bar, and cells irradiated with 830 nanometers is shown with the black bar. Irradiation at both wavelengths significantly increased enzymic antioxidants superoxide dismutase, heme oxygenase, and catalase. The superoxide dismutase is the graph on the top left, heme oxygenase on the graph on the top right, and catalase the graph at the bottom. This study showed that PBM at 660 and 830 nanometers alters the AKT FOXO1 signaling pathway and attenuates oxidative stress by increasing the levels of antioxidants. A wavelength of 660 nanometers was slightly more effective than 830 nanometers in regulating the AKT FOXO1 pathway. Photobiomodulation works on the principle of low-energy biostimulation, causing photochemical reactions in cells and tissues. Earlier studies showed that the best wavelength and fluence to use in these in vitro models was visible red light and near-infrared light with a fluence of 5 joules per centimeter squared. There's increased viability, proliferation, migration, fibroblast differentiation, there's decreased apoptosis or cell death, and inflammation. The electron transport chain in the mitochondria was stimulated, and the activity of cytochrome C oxidase is increased, as is the production of ATP. There is also an increase in intracellular nitric oxide and reactive oxygen species, and appears to be a photochemical process since these molecules were seen to be increased immediately post-irradiation. PBM enhanced the synthesis of various extracellular matrix proteins, including collagen and TIMP, which inhibits our MMPs. Our MMPs were decreased, and those are the molecules or the proteins that degrade our collagen. There's an increased release of epidermal growth factor, and increased proliferation, viability, and migration in response to stimulating the JAK-STAT pathway. There's also an increase in antioxidant enzymes and stimulation of the AKT FOXO signaling pathway, promoting cell survival. This research is continuously building on and refining the story of photobiomodulation. These studies have contributed significantly to the body of knowledge of PBM on diabetic wound healing and have shown that PBM in the visible red and near-infrared range has a definite therapeutic influence on diabetic wounded cells. Just a big thank you to all the funders and sponsors for these projects throughout the years. And of course, without their contribution and funding, none of this would ever be possible. Thank you for your attention and giving me this opportunity to show you and share you some of the work that has been done in the Laser Research Centre. And remember, where there is light, there is hope.
Wow, what a fantastic presentation. Good evening, Professor Mpedi, Professor Khan, Professor Houreld, distinguished guests, colleagues, Mr. and Mrs. Houreld, Mr. Kenning, Gemma, family, friends, and students and colleagues who have attended tonight. Photobiomodulation. What an impressive word for a very simple process, light therapy. And although this term was only coined a few years ago, the idea of using light to heal or treat disease conditions has been used for thousands of years, with evidence from the ancient Egyptians using sunlight to treat diseased conditions. Indeed, the level of sophistication has evolved significantly, but the basic premise of photobiomodulation remains the same, using light to heal. How elegant and insightful was Professor Houreld's address tonight. In a very sophisticated fashion, she explained what has become a part of her life's work, investigating the molecular and cellular effects of photobiomodulation on diabetic wound healing. Considering the incidence of diabetes worldwide, as well as the significant increase in expected cases of this dreaded debilitating disease, research to secure prevention and treatment is an international priority. Nicolette's research not only addresses an improved treatment modality for one of the consequences of diabetes, diabetic ulcers, but it also provides significant evidence of the mechanism of action of laser irradiation and thus exactly how photobiomodulation induces biochemical pathways and activates signaling molecules to enhance and secure successful healing. I believe I would not be exaggerating if I say that the work that Nicolette has done on the nitric oxide and JAK-STAT pathways, for example, are groundbreaking work and provided the foundation for further investigation worldwide. Her work has been published internationally and her global stature is evident from the many invitations she receives to address international audiences. She is also the president-elect for WALT. Locally, she's been honoured by the National Research Foundation as a C1 rated scientist. I've known Nicolette for 25 years, from undergraduate student to postgraduate to postdoc fellow, lecturer, senior lecturer, associate professor, and tonight, the pinnacle of her academic career, full professor. On a personal level, Nicolette has been a very dear friend, confidant, one of the most reliable people that I've ever known. We've travelled the world together, met unbelievable scientists, shared our work together, and made quite a few memories together. That I won't share tonight. She has walked the path with me to build a successful research centre while specialising in photobiomodulation and becoming one of the utmost experts in wound healing in the world. We have laughed and cried together, shared successes and failures, and as a friend I will forever be grateful for that. Her intellectual superiority is beyond question, but what has made Professor Houreld especially valuable is the research centre, and much love, health and happiness for your future. Thank you.
Thank you. Earlier on, I talked about Ingubo, the rope being assumed after the presentation. That moment has arrived. I would like to invite our Executive Dean, Professor Seham Khan, to please rope Professor Houreld.
You keep that for me, please? I nearly forgot.
They say healers must heal, preachers must preach, teachers must teach. I can go on and say farmers must farm, and professors must profess. I'm sure you'll all agree with me that tonight we have heard Professor Houreld profess. Professor Houreld, congratulations. Just listening to you, watching you, I said to myself, I know nothing about laser healing. I'm curious. I'm sure many people at home are curious about laser healing. But sitting here as an academic, I said to myself, the future looks good. Because here is another colleague joining the ranks of professors at this university, in South Africa and the world. And we can only continue to say Viva Academia, Viva Professores, because we know this is not the end. Without new professors joining the ranks, then the academy will be lost. This is what I'm saying. So from my side, the future looks good, and thank you very much for that. Congratulations, Professor. Ladies and gentlemen, this kind of achievement is not easy. Otherwise, there will be many professors, and this would be a worthless title. But because it's hard, it's not easy, it's something that takes guts, hard work, sacrifice, and it's something that we should celebrate. And this kind of achievements, ladies and gentlemen, are not the kind or the type of achievements that one achieves without the encouragement and support of loved ones. And tonight, I would like to thank all those that supported Professor Houreld here, including family, friends, and colleague here, and our colleague here, Professor Abrahams, and many other people, because this journey, without this kind of support, you can easily give up and say enough is enough. So I thank all of you. Being a professor, I can tell you, is I wouldn't say thankless. To others may look thankless, but to us we know it's a higher calling. We've got a contribution to make and a difference to make. And this reminds me, colleagues, ladies and gentlemen, of one of my former deans that used to say the rewards of a professor are in heaven. But having listened to Professor Houreld tonight and showing how the light is used to heal, I think seeing people being healed like that, you can already see the rewards here on earth, Professor, before even going to heaven. I will not tell you what I used to tell the good professor. Well, I can share with you, not to leave you curious. I used to say that presupposes that all professors will go to heaven, and I'm not sure about that. But anyway, as I said, this is not something that you can achieve alone. You need leaders like Professor Seham, the Executive Dean of the faculty, to provide an environment where colleagues can flourish. And Professor Seham, thank you very much. Leader is not seen by how a leader looks good. It's about how those that support, that surround the leader, thrive. Prof Abraham, I will say the same to you. Congratulations and thank you. The success of a leader in his or her field is not seen by how good one looks in front of audiences. It's about those that he or she supports and nurtures. And that way, as I said earlier, the future looks good because they're going to take the baton and run with it and secure our academy, our calling. I would like to thank you once again, Prof. Abraham, as our respondent this evening, for taking such and fulfilling such a wonderful role. It means a lot to us. We don't take that lightly. I would also like to thank our audience at home, watching via Facebook, watching via YouTube. We don't take your support lightly as the University of Johannesburg. We thank you for that. Last but not least, there are people that do a lot that you never get to see. The unsung heroes, people who work behind the scenes. I would like to thank you from the bottom of my heart for making this event possible. People will never see you, but I see you, and I thank you. It comes from the bottom of my heart. Ladies and gentlemen, we hope that we'll see you again at one of our events. For now, I would like to say COVID is real. Please stay safe and healthy. Thank you.